Hello all. Now in today's sessions we will discuss how to calculate the diameter of shaft. Okay. Now here are some examples of shaft. This is the propeller shaft, which we can with the help of this propeller shaft we can transmit power from engine to axle. Then this is the crankshaft of IC engine. Then we have hydraulic turbine shaft, and then this is the steam turbine shaft. Now basically, when shaft is subjected to some kind of torque, we have to determine how much torque it can sustain before its failure. Okay. Now, when failure will occur, suppose say we have power transmission 100 kilowatt, and that torque transmission capacity of that shaft is only suppose say 150 Newton meter. Now, whether we have to identify for that 150 Newton meter the requirement of diameter we should know. If the diameter is required, say 50 mm, and we are designed that shaft for only for 40 mm, below that 50 mm, definitely this shaft will get failed. Okay. So to avoid the failure of shaft, you have to identify the dimensions for that particular torque. Okay. And we can determine the diameter when shaft is supposed to be solid shaft. We can determine the diameter when shaft is supposed to be hollow shaft. If you look at this arrangement, basically in turbine shafts, hydraulic dam, we are using hollow shafts to transmit power from that turbine to generator. Okay. And we have to identify how much diameter is required to sustain that particular load before its failure. Similarly, if you look at that steam turbine shaft, again, there is a step type of shaft we have used. So depending upon the requirement, one can define the diameter for particular application. Okay. Now we'll take that example, and based on that example, we'll discuss what should be the diameter for particular application, diameter of that particular shaft for application. Okay. Now let's take this example. Suppose say the power requirement is given. So let's consider this problem statement. Determine the diameter of solid shaft which will transmit power of 275 kilowatt at 300 rpm. The maximum shear stress should not exceed 30 Newton per mm square, and twist should not be more than 1 degree in shaft length of 2 meter. The modulus of rigidity of material is given 1 into 10 raised to 5 Newton per mm square. Okay. Now what data we have? We have power, that is 275 kilowatt. We have speed 300 rpm. Then we have tau, shear stress is given. It should not exceed 30 Newton per mm square, and theta value is given 1 degree for the length of 2 meter. And modulus of rigidity, that is G value is available, which is 1 into 10 raised to 5 Newton per mm square. So our first aim is we have to determine the value of torque based upon power. Okay. So we can write power is equal to 2 pi nt upon 60. Okay. So that power they have given in kilowatt, we have taken that power into watt. So 275 is equal to 2 pi, speed is 300 rpm into torque upon 60 into 1000. So you'll get that value of torque in Newton meter. So the value of torque is 8.754 into 10 raised to 3 Newton meter, which we can convert that value of Newton meter into Newton mm, which is 8.754 into 10 raised to 6 Newton mm. Okay, that is the value of torque. Now, once we get that value of torque, then we can use that correlation between torque and shear stress. So what is that correlation? Tau by R is equal to T by R. That is tau T by R is equal to G theta upon L, which is equal to tau by R. That is the correlation. So what we have? We have torque, we have R. We can equate that value of tau is equal to TR upon J. So torque value we have, then radius we have, J value we can calculate, polar moment of inertia, which is pi by 32 d raised to 4. So we can put that value of shear stress. Shear stress is given that shear stress should not exceed 30 Newton per mm square. So you can put that value of tau max 30. Torque we have already calculated 8.754 into 10 raised to 6. Then radius is half of the diameter, that is d by 2, upon J value is pi by 32 d raised to 4. So we will get that value of diameter based upon this shear stress. So if you put all these values, then you will get diameter of that particular shaft 114.12 mm. Okay. Now again we will calculate diameter based upon angle of twist. So we are using two criteria to determine the diameter. First is diameter based upon that shear stress, and second is diameter based upon angle of twist. Now look at the value of theta. So theta we have 1 degree. Take that value in radian. 1 into pi by 180. So theta is equal to torque into length upon modulus of rigidity into polar moment of inertia, that is G into J. So torque value we have 8.754 into 10 raised to 6 Newton mm. Length we have 2 meter, that is 2000 mm, upon G value 1 into 10 raised to 5, that is rigidity, modulus of rigidity, and J value pi by 32 d raised to 4. Now it is a solid shaft. That's why we have taken that J pi by 32 d raised to 4. Again, if you put all these values, then we'll get diameter. So that diameter is 100.54 mm. Okay. Now the question is which diameter we have to consider. Okay. So for shaper size, we have to consider diameter which has larger value. Okay. So to avoid its failure, we can take maximum value for that particular power transmission, and the maximum value between that shear stress and angle of twist, we have more value diameter based on shear stress. So you can take that diameter 114.12, you can round up that value. So you can say that diameter required for that particular power transmission is 115 mm. Okay, this is the first example. Now look at the second example. Again, suppose say instead of solid shaft, hollow shaft is given. Now look at the problem statement. Hollow shaft with the diameter ratio of 3 by 5 is required to transmit 450 kilowatt at 120 rpm with uniform twisting moment. The shearing stress in shaft must not exceed 60 Newton per mm square, and twist in length of 2.5 meter must not exceed 1 degree. They calculate the minimum external diameter of shaft satisfying this condition and take the modulus of rigidity 8 into 10 raised to 4 Newton per mm square. Okay. Now what we have hollow shaft. Then again power is given, speed is given. Then we have the value of shear stress. Theta is given, length is given, and modulus of rigidity is given. Now first we will find out torque. So power is 2 pi nt upon 60 into 1000. We can take that power 450. Speed is 120 rpm. So 450 is equal to 2 pi into 120 into torque upon 60 into 1000. So you get that value of torque. So what is the torque value? 35.81 into 10 raised to 3 Newton meter. Convert that value in Newton mm. That is 35.81 into 10 raised to 6 Newton mm. Now again we will use two criteria. One is based on shear stress, diameter based on shear stress, and second is diameter based on angle of twist. Now we can put that values. So tau max is equal to torque into radius upon J. Now what we have, there is a ratio of 3 by 4 is given. Okay, so di internal diameter is 3 by 5 do. That relation is given. So you can write internal diameter is equal to 0.6 times outer diameter. So you can put that value and we can find out correlation between that internal diameter and outer diameter. So you can write J is equal to pi by 32 OD raised to 4 minus ID raised to 4. Outer diameter raised to 4 minus inner diameter raised to 4. So if you put that value, then you will get J value 0.08545, outer diameter raised to 4. Okay. So you can put that value. So tau is available 60 Newton per mm square. Shear stress did not exceed 60 Newton per mm square. So you can put that tau value. Then we have torque 35.81 into 10 raised to 6. Then radius is half of the diameter. We are taking outer diameter d0 upon 2. Okay. Upon we have that value of J, that is 0.08545 d raised to 4. So to put all these values, you will get outer diameter, which is 152 mm. Okay. Now in second case, diameter based on angle of twist. Again, theta is given in degree. Convert that value in radian. Theta is equal to torque into length upon G into J. Torque into length upon modulus of rigidity into polar moment of inertia. So we have theta 1 degree, 1 into pi by 180. Torque is 35.81 into 10 raised to 6. Length is given 2.5 meter. Convert that value into mm, 2500 mm. Upon G value is available, modulus of rigidity, it is a G value, 8 into 10 raised to 4 Newton per mm square. And J, that is polar moment of inertia, 0.08545, outer diameter is to 4. So we are getting outer diameter 166 mm. So based on this angle of twist and shear stress, we can say that for safety of that shaft during power transmission, we can take larger value to avoid the failure, that is 166 mm. So in this way, we can calculate diameter of shaft based on shear stress and angle of twist. Thank you.